This is the first 8 slides of the molecular structure and bonding unit, and it's mostly a revision of first year material where we look at Lewis structures. And so I'm going to remind you about Lewis structures. You've done them extensively in first year. I'm not going to cover them extensively here at all. You need to revise the procedure for drawing Lewis structures. You need to revise resonance structures, and you need to revise a procedure for the calculation of formal charges. Okay, so in the table that's given, you will see and you will remember that there are certain resonance structures like the phosphate ion, the sulfate ion, the perchlorate, the sulfite, nitrite, the ozone, all of those ones that you see there, those are really simple ones. You need to know how to do this. It's important so that you understand where we're going with bonding later on. Okay, just some revision in terms of terminology. We know that a bond is a sharing of electrons. Lone pairs are non-bonding electron pairs. The octet rule is a requirement where we need 8 electrons that surrounds the atom, except for hydrogen and the other elements that do not meet the requirements to satisfying the octet rule. The expanded shell is when the octet rule is broken for a central atom. It usually occurs with elements from the third period when we start with the d orbitals. And expansion of that octet can include between 10 and 18 possible electrons. There are higher numbers, but it's very rare due to crowding. Resonance, reminder that this is more than one Lewis structure that's possible. And then, of course, there's one more word, isoelectronic. This means that molecules have the same electronic structure. Their Lewis diagrams are the same, but they have different central atoms. With regards to formal charges, this procedure helps us to assign the bonding when there are several possibilities. The equation is given on the slide. As you can see, the formal charge is equal to the valence electron for the free atom minus the number of lone pairs electrons minus the number of bonds to the atom. And the charge on the molecule and the ion must be equal to the sum of all the formal charges. There are a couple of rules that you need to remember, that there are structures minimizing formal charges. You need to place the negative formal charges on more electronegative elements. And there is smaller separation of opposite charges tends to be favored for adjacent atoms. So the result of this then is that bonds with large polarity are very much more stable, and atoms with a very large electronegativity difference are likely to be bonded to one another. So here is a table which shows some compounds with their Lewis structures and the original formal charge, and then there's others that show how the formal charges can be minimized and where the formal charges would sit. You can go through this in your own time and practice with these examples. Figure out where the formal charge goes. Okay? This is entirely up to you, and you need to revise this material. I'm not going to teach it again because it's been taught already. It's prior knowledge. You're required to know it. Okay. Remember that there are some exceptions and some unusual behavior. So we see this particularly with beryllium and boron. It seems to require multiple bonds to satisfy the octet. However, we know that formal charges indicate otherwise. And so what we find is that in this instance, if I point this out to you, we would draw the Lewis structure here for BeF2. However, in the solid state, this is what we actually see. We see like a very complicated polymeric structure. And similarly for BeCl2, we find that we get dimerization taking place. Okay, so the formal charges on these actual materials, you'll see actually work out a whole lot better. Okay, there's noticeable changes in bond lengths as a result of these exceptions and unusual behavior with boron and beryllium. So in this case, we've got boron trifluoride. We find that the BF bond length is a lot shorter than the actual calculated single bond length as indicated. So what this means is that the resonance structures actually help us understand that that electron density of the double bond is delocalized over the entire structure, and it tends to pull the atoms closer to one another and hence shorten the bond length. So this is really all that I'm going to cover with regards to Lewis structures. The material that you have to go over in terms of drawing them and formal charges and explaining exceptions needs to be revised from your first year work.